Our first speaker for the day is Amir Al-Sudani. He's a postdoc with the Mississippi State University. He is working under Nico Quintana, the economist with NCAR. And we are going to pull it back up. Oops. And take it away.
All right. Thank you very much. Good morning, everyone. Thank you for being here on my presentation, which is part of my project with Dr. Quintana. So in this presentation, we're going to explore the role of off-season precipitation and irrigation water on the change in depth water in Mississippi Delta. I pressed one wrong.
Did you press the mute?
No,
mute the screen? Okay, hit it again.
Here?
And so just use the side arrows.
The Mississippi River alluvial aquifer is the main source of our irrigation in the area. So it covers around 32 square miles of Arkansas, Kentucky, Louisiana, Mississippi, Missouri, and Tennessee. 22% of this aquifer located in Mississippi, which is about 7,000 square miles. The MDR is one of the, actually this aquifer underlies the most part of Mississippi Delta region. The MDR is one of the largest and most diverse agricultural production areas in the United States for row crops production, such as corn, rice, soybean, in addition to cotton, sorghum, wheat, and catfish. Oh. I don't know.
Oh, there you
go. Yeah. On average, NDR received about more than 52 inches of rain during the year, but most of that rain occurs outside the growing season. From 2014 to 2017, around 65% of that rain occurred outside the growing season, from October to March. So for that reason, MDR depends on irrigation to sustain the agricultural production, most of which is on row crop production. So the Mississippi River Valley aquifer is the main source for this irrigation in MDR. According to Mississippi Department of Environmental Quality, from 2000 to 2022, the wells permitted increased from 10,000 to around more than 21,000. With yearly new permits, wells range between 178 in 2003 to 1,000, around 100 permitted wells between the years 2011 to 2013. So because of that, there is an increase in pumping rate from the aquifer, which is resulting in depletion in this aquifer. So from 2000, you can see here in this, from 2000 to 2020, there is a decrease in groundwater level, which is ranged between 2 feet to more than 14 feet. There is a heterogeneity here you can see in the depletion in the aquifer, which is maybe this interesting for the hydrologist, why this happened. There is some, especially in the middle of the center of the region, there is a high depletion in the aquifer during this year, this time period. The main source of the depletion in the aquifer, which is the water used for irrigation, which is either increase in number of permitted wells, or expansion in irrigated acreage, or increase in water use, which is, or the combination Yes. On the other hand, the precipitation, it can help to reduce this depletion in the aquifer. Through, we can distinguish between two times for the precipitation. So we have an on-season precipitation, which has indirect impact on the groundwater depletion through decrease the water use for irrigation. Also, we have the off-season precipitation. Also, it has direct impact on the aquifer and as a recharge. So through the infiltration and percolation. We aim in this presentation, we have two objectives. The main objective is to use the reported water use data to quantify three margins, which is the total water use, irrigated acreage, and also the water applied per acre, which is what we call here the extensive margin or intensive margin, or the total response. And response to change in depth to water and also to climate variables. The other objective we need to quantify the impact of water use and precipitation on the change in depth to water. So we'll see that we'll take 2 points for 2 years from the same time during March and see the change in depth to water. Between these 2 time period, we quantify the precipitation and also the water use and how the role of these two factors can impact the change in depth to water. So in our model here, the first objective is to quantify these three models, which is the total water use, is the big W, and the A is the number of irrigated acreage, and also the W, the small w, is the water applied per acre. So what kind of factors we include in this model, which is here in equation 1, which is we have the weather condition, we have depth of water, we have soil, and some other variables. Also, we include the field fixed effects and time fixed effect to control for any change during the time and the space. The other objective is to quantify the change in depth of water in response to total water use and the precipitation. So in this, sorry, this should be equation 2. So here we assume the change in depth of water in year T is a function of the total water use, T-1, and also the precipitation in T-1, and also some other variables, which is like soil type, and also the change in the depth of water in T-1, which is, it can be related. So from equation 1, if we take change the depth to water from T-1 to other side, so we get the equation 3, which is the change in depth to water, which is a function for irrigation, total water use, and precipitation, and some other variables like the soil type. So here for the change in depth of water, as I mentioned, I'm taking two, just to clarify here the change in depth of water. I'm taking 2 points for the well, 2 measures during March or April, which is why I'm taking these 2 in this time, because in this time we make sure there is at least a minimum use of groundwater in this time. So there is instability in the ground and the water level. So we take the measures for these two points for time t and time t-1, and then subtract time t from time t-1 So to give the change in depth to water on time t. So, and then this change in depth to water affected by factors which is before time t, which is the total water use and also the precipitation. So for the change in depth to water, we include some spatial impact for the change in depth to water, because at each point when I'm taking the measures, there's an area can impact this point, not exactly the same point. So in this case, for this analysis, I'm taking the 1 kilometer zone, which is, it can impact this point of the change in depth to water. So this include in this 1 kilometer, we calculated the total water use in that 1 kilometer, and also the precipitation, the average of the precipitation also in the same, some other factors. So all variables in this model will be in 1 kilometer zone. So the data we have, so we have voluntarily reported data from farmers. So this is from 2014 to 2017 for about 4,500 groundwater per users. So we use this data. We have the total water use, and we have also the irrigated acreage for each pair. So we use it. So this represents around, I think, around 10 to 12,000, 10 to 12% of the total permitted on that these 3 years. So this data is 10 to 12% from the total, because this is voluntary. So not everyone has to report what he is doing. So other data set, we got some from the hydrology variable depth to water from USGS, and also the climate from the present data set and USGS. So we can see here in this table just kind of information about the data we have. This is the 4,500. So for the total water use, we have the mean is around 80 acre feet, and with the minimum is around 1 acre feet to more than 1,000. And also the irrigated acreage we have range between 6 to 765 acre, and also the water applied around between 0 to more than 10 feet per acre. So because we have in this data set, not only the row crops, because also we have rice, also which is the more intensive crop in terms of water use, and also we have fish culture, which is also use more water. So this is why we see here there is the maximum is around more than 10 feet per acre. So the estimation here, so we have as I mentioned, that we have three for the first objective. So we have here three regressions, which is the total water use in the column 1, and extensive margin, which is the irrigated acreage, and also we have the intensive margin, which is the water applied per acre. So from that, what we need, we'll focus on, I will not focus on all variables, we'll focus on 2 variables, which is depth to water and precipitation. Precipitation during the growing season here, which is from April to August. So we can see here the depth to water in terms of the total water use and water applied per acre. There's a negative impact. This means when the depth to water like increase, so farmers willing to apply less water on, use less water. Why? Because the pumping cost. Because two things it can account for the pumping cost. Two main variables, which is the energy price and also the depth to water. So in this case, we can see which is makes sense. For the precipitation, also we have when we have more precipitation, farmers willing to use less water, also because it can use for that. So we can see here for the irrigated acreage and also for both for depth to water and precipitation. In fact, people willing to adjust the irrigated acreage for a long time, they will not adjust the irrigated acreage for the recent weather condition or depth to water. They need for at least 5 years. This method, many literatures found that in terms of depth to water and also in terms of precipitation to adopt the change in climate. They need at least 5 years. So in this analysis, I didn't put like 5 years that. So if we went to do more analysis in that, so we need to include at least 5 years, sometimes 10 years lag of the average precipitation to see the farmers, like after 5 years of concern of the precipitation, if they will adjust the irrigated acreage. But we can see here on the opposite when the water applied. So farmers can adjust the water applied right away. When they feel that like there is an increase in depth to water, maybe they will adjust the water applies to decrease the pumping cost. Also for the precipitation, once there is a good precipitation during the season, they will adjust the water applied, which makes sense. The other objective which is the change in depth to water. Here I include the total water use and also the off-season precipitation, which is from September till March. September, October, November, and January, February, March, the other year. So we have this time period between two points. From the end of the season in year T minus 1 till the beginning of the season of the other year. So here also I include two variables, which is sand and clay. Maybe it can affect the population, filtration of population, which is, as we can maybe in here, I don't know for the hydrologists agree with that or not, but this is the main thing I can do for this analysis to include the soil type, because the soil type also has impact on the water movement. So also what I include, so as I mentioned, this analysis is within 1 kilometer distance from the well, the groundwater diversion. So also I include the surface water permits within also 1 kilometer. How many surface water permits like within this distance, and also how many groundwater permits. Also I include within that 1 kilometer, if that permit, there is Mississippi or Yazoo River, which is these the two main rivers within that distance. This is dummy variable. There's a river inside that 1 kilometer. There is one. There is no zero. So the other dummy variable, which is other river, other than Mississippi or Yazoo River, there is a small river or creek or something like that inside also this boundary. So also we give them 1, otherwise 0. So from these, I will focus on As I mentioned, for the objective, we focus on two things with the total water extracted and also the precipitation during that time period from September, which is the off-season precipitation. So we can see here. Here I included three analysis. So the first column, which is the total water use. I forgot to mention, in this analysis, I used the 4,500 observation to predict the land reported, because as I mentioned, we have around more than 60,000 permitted during that time period from 2014 to 2017. So we have only 10 to 12% reported. I used that reported permit to predict the behavior of the non-reported using the same variable, which is the climate and depth of water for each permit. And then from that, so for this analysis, we have around 61,000 observation for this analysis. So the first column, I use the total observation, which is the 61,000. Then from that, I split my data set into two data sets based on depth of water. The depth of water in Mississippi, that in the aquifer ranged between around 2 to around 60 feet. So I split that data into, based on the depth of water, in two groups. One group, the column one, which is if the depth of water is less than 30. Column 3 is the data set where the depth of water is more than 30, to see if there is any heterogeneity in response to that based on the depth of water. So the first table for the total water extracted. So we can see here also there is a heterogeneity between the when we submit the data set in response to total water extracted. So we can see here always when we have less depth of water can affect it more in terms of the total water use and also in terms of the precipitation. The only thing in the precipitation, the off-season precipitation, we can see here when we have the depth of water is more than 30, there is an impact from the precipitation on the change in depth of water, but it's not significant. Maybe this would need more analysis why it's not significant. The precipitation doesn't have that much impact when with the deep aquifer. So we did some calculation for that, because this table, these two tables, sometimes will not give a little sense for audience. So we did some calculation to convert these numbers to something maybe it's easy to capture. So from that, for each 100 acre feet increase in water use, so the depth to water will increase around 0.65 feet. So if we go back, what this means? This means the 100 acre feet, this is not for the whole data set. This is on average. This means for each permitted, for each groundwater users, if they increase the water use by 100 acre for each point, there's an increase in depth of water by 0.65 feet. On the other hand, also for the precipitation, for each 4 inches, an increase in, it's more than the average. For each 4 inches increase in precipitation, the change in depth of water will decrease by 0.19 to 0.2 feet. So even from that, we can see there is a difference between the water extracted and precipitation, which is maybe the water use has more impact in terms of the recharge. So also we can see here there's also the change when we split the data between like when the depth to water is less than 30 and depth to water is more than 30. So what we concluded from this this analysis. So depth to water is the main determinant on water applied for per acre and total water use. So on-season precipitation play an important role on season. Why? Because it has impact on water use. Maybe it doesn't have that much impact because maybe we assume most of the water from the rain during the growing season we consume from the crops, but it has indirect impact on depth water, which is decrease the water use for irrigation, and also so it can keep to maintain a little the groundwater level. So also we can see the off-season precipitation has significant impact on recharge in the aquifer. Maybe it can help for farmers, for example, to put like storage, to get some storage in the on farm and use that off-season precipitation for use after that when there is a shortage in the precipitation. So also we learned from that there is a change in depth to water also is related how deep the aquifer. If the aquifer is deeper, like more than 30, as we mentioned here, so the change, the reaction to precipitation, the off-season precipitation is less than when we have the depth to water is less than 30. So, any question?
Any questions in the room or on chat? Or in the audience?
I have a question.
Yep.
So you're using precipitation as a predictor for some of your response variables there. Do you have any work planned in terms of maybe a model estimate of groundwater recharge? So like something that's more connected to how precipitation actually contributes to groundwater. Because presumably a lot of precipitation is lost to runoff.
Right. So this is what I mentioned in that. So as an economist, this is what we do. But in terms of to complete that, so to be like a good model, it should be there is a hydrological components in this model. So this is why I always be careful when I'm talking about these, because always I mentioned this is not 100% guarantee because there is some other factors. Like I mentioned, infiltration, percolation, so the soil type, water movement. So, but this analysis gives like initial indication. So this is why when I split the data set into two data sets, when we're talking about how deep the aquifer, we see the off-season precipitation. Maybe it takes longer to reach the aquifer, or maybe there is some other like water movement. So this is why we can see here the off-season precipitation has impact, but it's not significant. When we're talking about like the depth to water is more than 30. So, but absolutely, it should be there is hydrological components, variables, including in this model to be like from both sides, from the economists and the hydrologists.
Thank you very much.
Thank you very much.